Right. So today, my dear students, we are going to learn a very essential lesson. You know that when you go to grade 11 science, this lesson, quantification of elements and compounds, this is the basement for many other backgrounds of chemistry. So I will elaborate the word quantification. If you go to the level of an atom, we have a problem. What is that? You cannot visualize the atom for the naked eye. And even measuring the mass of an atom, mass, you know, the amount of matter present inside that. The mass of an atom, measuring the amount is so hard. The reason it's not visible to the naked eye, as well as that mass is very tiny. Generally, the mass of an atom, you can see now, the mass of a single atom, one atom of carbon, is this much of value. So measuring the mass becomes a very large obstacle for the development of science in the centuries ago. So they were able to design a certain concept to measure the mass of an atom not by kilograms, by another scale. So in this lesson, the whole lesson is based on those type of calculations. So let's see what we have in this lesson. Right. First thing, we are going to learn how we measure the mass of an atom not by grams or kilograms, because it's very tiny. If you measure in that scale, we have to create a new scale. So to create that scale, we need a standard. So you can see here in this figure, in this slide, you can see measuring the mass of an atom in kilogram is extremely very small, a small value. So see the values, minus 23 grams, it's very tiny. Carbon, sodium, chlorine, potassium, all these are very tiny, and their masses are in gram scale or either in kilogram scale is very much tiny. So we have a problem now, how we measure it. Remember this like a story, then you can analyze this and remember forever how that was measured. So let's see. This is a simple lesson, learn carefully everything. Right. Assume that you want to measure the mass of an atom, but not in gram scale, because if you measure it in gram scale, it is very tiny. We have to develop another unit. So how they develop this, it is mentioned here. So let's see this thing. I'll explain it as an example. You know that the atom is made of subatomic particles. Now you can see the three different subatomic particles, the electron, proton and neutron. Recall your memory and say, what are the two subatomic particles that develop the mass of an atom? That is the proton and the neutron, not the electron. Why? The electron mass is very tiny compared to the mass of the proton or the neutron. So what we have the idea here, we want to measure the mass of an atom in different unit, not by kilogram. For that we need a particular scale. To develop the scale, they use a word atomic mass unit. Here I will elaborate the word atomic mass unit. It means number of units that the atom is made of. That means in here, for example, I will get a wall, a brick wall. The total mass of the brick wall is 1000 kilograms. Right? Then what we're gonna do? We want to measure the mass of one brick. That will be the mass of one atomic mass unit, similar to the atom. Assume that wall is the atom, built up of small subatomic particles, the protons and neutrons. Those are the units. So we want to measure one mass of one single unit. So what we're going to do? total mass of that wall you divide by the number of bricks. You can count the number of bricks. Then you get the mass of one brick. So that is the standard thing they did for here. They know that they found the mass of the carbon-12 isotope in grams. Then what they did? They know that the atom carbon is made of 12 nucleons. I will tell the word what is a nucleon. Nucleon means neutrons and protons together called nucleons because they are found in the nucleus. So 12 nucleons, 6 protons, 6 neutrons are present. So if you divide the mass of that carbon-12 isotope atom by 12, then you get the mass of either a proton or a neutron. So that number is in grams. That is the atomic mass unit. So why we want this? What is the reason to measure that thing? The mass of one single nucleon. We know that all these atoms we study in this world are made of these small units. Now, why we need this? We know that if you have a new wall, a brick wall, I will get the same example again. There's a brick wall, made of same type of bricks because all the atoms are made of same type of protons and neutrons. The same way, that new wall is made of same type of bricks. So what we're going to do? We are going to find how many bricks are there. How many atomic mass units are there for that atom. That will be the new scale to measure the quantity of matter in an atom. That's why I told you we can't measure it in grams. We need another scale. That scale is atomic mass unit. If you have that scale, assume that that example I mentioned here, you have a new brick wall containing, assume that it contains 1000 kilogram amount of bricks. One brick has a mass of 10 kilograms. Then obviously you know that how many bricks it will contain. It contains 100 bricks. Like that, we found the mass of one unit. Then what we're gonna do? We're gonna find out the mass of another element in atomic mass units, and that is taken by this method. So let's see what we get here. You take the mass of that atom, not carbon, any other atom. Then divide it by this number. This is a standard number we call atomic mass unit. Then you get the number of units that new atom is made of. So that is 1/12 mass of carbon-12 isotope. Or I will say atomic mass unit. If you divide the mass of an atom, it's in grams or kilograms, by the atomic mass unit, this number, you get number of units present in that atom. Again I am saying what are units? Protons and neutrons. But we take it relative to carbon. So that's why we have adjective here, relative atomic mass. This relative atomic mass, now you can see mass of the atom is in grams. AMU, that we call atomic mass unit, that is also in grams. So to gram and gram cancel out, you don't get any unit for this relative atomic mass. It's just a count. That's why the lesson name quantification. We are counting the number of particles the atom is made of. Now we have the idea what is we call relative atomic mass. Now we go for an example how we actually calculate this. Actually, they don't ask you to calculate this thing, just asking you to remember or just to get the understanding how the way of calculation. So just get the understanding. For example, I will zoom that up. You can see now how they calculate the relative atomic mass of oxygen. Again I am saying to whom be relative? It's carbon-12 isotope. 1/12 mass of carbon-12 isotope. So let's see this thing. We take the mass, original mass of oxygen atom in grams. Then what we do? We have a standard number, that is the atomic mass unit. that is that previous number, this one. You divide that value, and you can see here they got this value by this substitution. So you can clearly understand that, I think. So from this you can see, and gram to gram cancel out. Now you can understand that you get an answer called 16.02. So solving is not necessary here. Get the understanding. Now you measure how many units of mass that oxygen is made of. That units are not in grams, atomic mass units. So atomic mass units, how many are there? There are 16 atomic mass units. They will be all the sum of protons and neutrons. See that? Very easy to understand. So this way they have calculated for each and every atom or the elements, they have calculated the relative atomic masses. What is the standard number they took? 1/12 mass of carbon-12 isotope. So the relative atomic mass can be defined as the mass of an atom with relative to 1/12 mass of carbon-12 isotope mass. Can you understand that part? So this is the table you can see in your textbook also. This is a table where we can see all the relative atomic masses are given for first 20 elements. In here you have a small doubt that 35.5 is there. All these values are round off values, but here we have a pending round off. We can't go to 35 or 36. It's between the value. You can't round off. If it is round off, it will be a larger error. So here it remains like this, but don't forget, this doesn't mean that there are half of the subatomic particle. There's no half of a proton or a neutron. It's just a number relative to carbon-12 isotope mass, 1/12 mass. So these are the standard numbers for relative atomic masses of each and every element in first 20 elements. So these numbers you get for the exam. Only thing is to just understand what is the definition for relative atomic mass. See that? Okay. So I will get one example. Just think about this. Lithium, a not common element we talk about. Lithium, the number 7 is a relative atomic mass. What do you mean by this number 7 now? You have to think about it. That's what we call the logical thinking. This 7 means there are 7 subatomic particles inside the nucleus of the atom. That will be, we have a problem now. We can't divide 7 by 2 because you will get equal number of protons and neutrons. That is not the thing. Sometimes it will be not the same. Even beryllium you can see, 11, you can see boron. You can't divide into, that means the proton and neutron numbers are different, but all together you have 7 subatomic particles in the nucleus. We call them, can you remember the name? Nucleons. We don't talk about electrons here. Now, why we want to know these numbers? If you go to a molecule, grade 8 or 9, you are learning about molecules. Let's see why we need these numbers we call relative atomic masses for further applications. Right, assume that we want to measure the mass of a molecule. Here also a molecule is also a tiny structure. You can't measure the mass straight by using grams or kilograms. We need that scale. What is its scale? Relative molecular mass. Here also we know why it is relative now. It's relative to what? Think about it. 1/12 mass of C12-6 isotope. So what we get here? We need to find the molecular mass relative to that carbon. So we have an easy case here. That is, assume this molecule hydrogen. Hydrogen is made of 2 hydrogen atoms. You want to find the molecular mass, but you can't find it is in kilogram or grams. We need that scale. So if you know the mass of one atom of hydrogen, there are 2, So straightforward, we can see you multiply the mass of one atom by number 2 because there are 2 hydrogen atoms. Then that will be called the relative molecular mass because it's a molecule. So you have 2 as the answer. Still here, no unit. Reason, it's a relative thing. Right? Not in grams, it is in another scale. Next example also the same. Nitrogen. Nitrogen contains 2 nitrogen atoms, the molecule of nitrogen. The gaseous molecule of nitrogen contains 2 nitrogen atoms. So take the mass of 1, actually we take the relative atomic mass of 1 nitrogen atom and multiply it by 2 because the molecule contains 2 nitrogen atoms. 28 will be the molecular mass, relative molecular mass of nitrogen molecule. So such a way you can find these 3. But if you go to the carbon dioxide, you can see here it's a little bit complicated than these molecules. So these are called homoatomic molecules. You can remember grade 9. Homoatomic means the atoms are the same in here. These are called heteroatomic molecules because hetero means the reason this molecule is made of 2 different elements or 2 different types of atoms. So how to get the molecular mass of this? Easy, but careful with the mathematics. Here carbon, the relative atomic mass is 12 because it's a sum, right? We are adding all the masses because molecule is made of atoms. What we're going to do? We add all the masses together to get the molecular mass. Right. 12 is the mass of carbon and you can see here this 2 belongs to O only. If it belongs to carbon also, we make a bracket and put 2. There's nothing here like that. So this 2 belongs to oxygen only. So that means 2 times 2 oxygen atoms relative atomic masses are there. Then you put a bracket and do it. Otherwise what will happen? You add these 2 and get 14 and you multiply 14 by 16. That's very wrong. Always use algebraic calculation methods to get the idea. Right? So that's very important. 2 times 16, 32. 32 plus 12 is 44. Still, there's no unit for this. And here a very good example mentioned. 6 times carbon atoms 12 plus 1 times 12. See the brackets. It's easy and it's very neat and very carefully we can calculate the thing without putting brackets. You get a mess in here. So don't be lazy. Put the brackets. It's safe to you to calculate this thing properly. So this is the way we calculate relative molecular mass for a certain molecule. Right. Now it's time for you to check your competency, that you have reached the competency level in this lesson. Calculating the molecular mass, actually relative molecular mass for each of these formulas. Right. I will explain a few of the formulas before we do this thing. I will go to, because in here if I zoom this up, you can see these formulas are easy to calculate. But I will get this thing for a while because some students will have a confusion. Why this hydrogen and here also hydrogen? That is due to the formula. This is methyl alcohol or methanol. It's a molecular arrangement or the formula of that thing. But actually there are 4 hydrogen atoms. So if there's a thing like this, how we add this? We start to take these things into the atomic combination ratio. It will be like this. I made this as CH4O. Why? I combine these 2 also. Because same element, no hydrogen. Now we can apply the solving formula here. See this? I applied like this. Carbon 12, hydrogen 4 times 1. 1 hydrogen is 1 and 16. Now you can solve this easily. You get the answer. 32. So that's the one type of question that combining this. Similar questions are there in that method. That is this one. You can see here. Because in here 2 oxygen atoms are there. You can just write C2 H4 and count the number 2O2. I mean O2 you can write. In that method you can just get the simple formula, empirical formula. From that formula you can get the answer easily. Otherwise you are confusing what we're going to do for here, multiply or add. No, always the sum we take. Right? Okay. Now I go to another example. Having complicated brackets like this, I will go to urea. So let's see in this one, you always remember the meaning of these numbers. This number 2, I'll zoom this up and say, this number 2 belongs to only for hydrogen. But why there's a bracket and a number 2? Because this number 2 belongs to both of them. That means you can make this into a simple formula, because it will get complicated otherwise to calculate. These are simple methods that I found. Now you can see here I just rearranged the formula into this empirical method, because I just write these two because they have no multiplication number, but this n has 2, so 2n are there, and this 2 times 2, 4 hydrogen are there. So you can just now apply the values 12 plus 16 bracket plus bracket, you get 14 times 2 plus close bracket and plus bracket 4 times 1 hydrogen. An easy case for this, right? Can you understand that part clearly? Simple as that. Like that you can find the values for each and everything. You can pause the video and find all the calculation parts of these things. So after that, in the next minute, I will apply the answers for these. So all the relative atomic masses are mentioned here. You can easily find the masses now. So pause the video and try to answer. Hope you got the answers now. So check the answers clearly. I'm just putting the answers. Right. Hope you got the understanding how to find relative molecular mass. Now we are shifting to a very important part, because you saw in the first page there was a person here. This name, this person, Amedeo Avogadro, very important person. Reason he found a very essential thing for the development of chemistry, I mean quantification of chemistry, that world, he found a very important thing. So let's see what he found. His name was Avogadro, Amedeo Avogadro. So he found very important thing, because you know the relative atomic mass or relative molecular mass has no unit. It's just a number. So he was able to design a method, a relationship actually, to give a unit for that number. To give a unit for that number, he just mentioned a very important thing. That is this. Get the understanding very clearly. Listen carefully. Assume that you have 12 grams of carbon. Why these 12 grams I took? The reason, this 12 is the atomic mass unit or relative atomic mass of carbon. See, 12 grams, for hydrogen 1 gram, for chlorine 35.5. See, this mass number is the relative atomic mass of that sample. If you measure 12 grams in the laboratory weighing balance, in that 12 grams, Avogadro says there are 6.022 into 10 to the power 23 atoms of carbon. Now we have another thing. We found atomic mass unit. Now there will be a confusion. Clear the confusion nicely. 12 means the number of protons and neutrons in a single atom, right? A single atom. If that 12 is related to 12 grams, that means not only single atom, there will be huge number of atoms. 12 grams is visible to us, carbon 12 grams. Inside that 12 gram, you have how many atoms? We have a problem. So Avogadro found a very important thing. He said that if there's a mass of a sample of an atom in equal number of to the relative atomic mass of that element, for example, relative atomic mass of carbon is 12. If you get 12 grams of carbon, exactly 12 grams, that means in that 12 grams you have this amount of atoms. Now here this is not a mass, right? This is the amount of atoms in that. So like that, this is the first stage of relationship he mentioned. That is, in a mass of a certain element with a number similar to its relative atomic mass will contain a standard number we call the Avogadro number of atoms. So this is the most important thing he mentioned, right? Then we go to next level of atomic arrangement, that is molecules. Even he mentioned, if you have a molecule, this is a very important thing because you will confuse the difference between these two. Get it nicely. In a molecule, now take the simplest molecule in this example is hydrogen. Hydrogen, if you get 1 gram, there are this amount of atoms. But here it's a molecule. Hydrogen molecules. We are going to find how many molecules are there, not atoms, right? How many molecules are there? To get how many molecules present in 2 grams, because 2 grams is the molecular mass of this hydrogen gas, not the hydrogen atom. If you have 2 grams of hydrogen atoms, molecules, how many molecules are there? He mentioned that is also equal to this Avogadro's number of molecules. But remember, this is not number of atoms. Assume that you want to get the number of atoms. How to get it? If the molecular mass is 2 grams, in that you have this amount of molecules, go for to find how many atoms build up the molecule. Here 2 atoms. If there are this amount of molecules made by 2 atoms, twice of this value will be the mass of, the amount of atoms in that molecule. Simple understanding like that. Right, now we get another example. Get this carbon dioxide. Why I took 44 grams here? 44 grams means 44 is the relative molecular mass of carbon dioxide. So here again I am saying carefully, don't forget this is not equal to atoms of carbon dioxide. There are no atoms in carbon dioxide, there are carbon dioxide molecules. In that putty you have carbon atoms and oxygen atoms. If you want to find the number of atoms of carbon or oxygen, we need to go for another calculation. But here it says a simple thing. How many molecules of carbon dioxide are there? In 44 grams, there are 6.022 into 10 to the power 23 molecules of carbon dioxide. Now we have the doubt how to find the number of atoms. If there are this much of molecules, how to find number of atoms? So we have a simple method to do this. Let's see what we're going to do here. I'm going to find some space to write. Now you can see I drew the illustration like this. Now you have 6 Avogadro number of molecules of carbon dioxide. First, if you want to find number of carbon atoms or number of oxygen atoms present, we go to the simplest ratio between them. Right? I mean not the simplest ratio, the exact ratio between them. You have 1 carbon is to 2 oxygen here. If the total number of molecules are this much, now simple mathematics. That means if the ratio is there, the ratio also related to this number. That means if you have this much of molecules here, there will be 1 times of that much of atoms of carbon in here. Similarly, if you have 2 oxygen atoms, If there are number of molecules are this much, that means you have twice of that much of atoms of oxygen to build up this whole amount of molecules. So you get the illustration like this very simply, you can find it out. Let's take another example to verify this idea. Now get this illustration here, calcium chloride. Now you write the ratio, calcium is to chlorine ratio is 1:2. Assume you have Avogadro number of, that means this amount of calcium chloride molecules. In that, how many calcium atoms are there? According to ratio, you can see it's 1. So 1 atom per molecule. So if there are Avogadro number of molecules, there should be 1 into Avogadro number of atoms. And here 2 into Avogadro number of atoms, because 1 per molecule of calcium chloride, you have 2 atoms of chlorine. So get the mathematical idea very cleanly. So you can say a relationship between them. If you want to find number of atoms, you have to find number of molecules present. We do some questions to get this idea confirmed, because using grams you can't directly find the number of atoms. You have to convert that into number of molecules present in that grams. Then Avogadro's last idea is this. Here in 12 gram set you have this much of carbon atoms. I'm now talking about the Avogadro's last concept. That is, if there are this much of carbon atoms, assume this is a set 6.022 into 10 to the power 23 atoms are there. Assume that this is a one set of atoms. He named the set equivalent to the atomic mass, relative atomic mass of that grams amount. He named that set as 1 mole. He named that set as 1 mole. What do you mean 1 mole? 1 mole is the amount present in a certain element or a molecule when you take a mass equivalent to the relative atomic mass or relative molecular mass of that sample. That means assume that you have measured 44 grams of carbon dioxide gas in the laboratory. That means in that sample you have two things to remember or get to find. One is number of molecules. Easy, because if you have molecular mass amount, relative molecular mass amount of grams, it should contain this much of molecules. Then how many moles are there? It's having 1 mole, because it's 44 grams. This 44 belongs to the relative molecular mass of carbon dioxide. So it should have 1 mole. So assume that 88 grams are there. So how many molecules? 2 times of this number. And how many moles? There are 2 moles. If you go to 22 grams, you measure 22 grams of carbon dioxide. How many molecules are there? Half of this number of molecules. And how many how many moles are there? Half a mole is present. If 1 mole set should have 44 grams, 22 grams means half a mole set. Right. Now you know that that's the molar mass thing we discussed, and that molar mass, now it should have a unit. So let's see why there's a unit for that. Because you know that if I say example, you have 12 grams of carbon. In that 12 grams, Avogadro told that there are 6.022 into 10 to the power 23 atoms. This atom thing, that means this number is either be atoms, molecules or ions. And he told us another thing. In this set, it's called a 1 mole set. That means if you have 24 grams of carbon, you have twice of this value and you have 2 moles. Right? So here, how to get this 12 is the 12 is the relative atomic mass of carbon. How to get this as molar mass? Because molar mass has a unit, grams per mole. So how to get this? You know one thing, in 1 mole there are 12 grams of carbon. That's why here it mentioned as 12 grams per mole. Per 1 mole there should be 12 grams of for carbon. For any other element, it's depending on the relative atomic mass of that element. For example, sodium, this 23 grams, if you measure 23 grams, it contains 1 mole of sample of sodium. That means it has this amount of sodium atoms, right? So that's the way. Only difference in here is the unit. You are calculating the normal trend, the normal method previously you learned. You are calculating the molar mass of these samples as the relative molecular mass. Then the ultimate thing, you are putting the unit like this. For example, I will get this thing, hydrogen sulfide, H2SO4, H2S, hydrogen sulfide. Now hydrogen is 2 times 1 because it's 2 i's of the atoms are there. So plus sulfur 32, you get here 34. Now this is the molecular mass. But now it is related to Avogadro's number, because if you get 34 grams of hydrogen sulfide, it should have 1 mole. So that's why you are putting the unit grams per mole. Right? In the laboratory, if you measure 34 grams of hydrogen sulfide, that should have a 1 mole or this amount of molecules. So like that you can calculate all these things. You can pause the video and calculate the relative molecular mass of each of them. But if they ask the molar mass without asking the molecular mass, the unit is essential. So hope you will do this and pause the video and check the answers after that. Now you can check your answers, check the answers properly. So these are the answers you will get. Right now, the last thing what we are going to discuss, that is, after learning all these relationships, final thing, these relationships build up a equation. Because you know that, I will recall briefly what we learned. You know that if we get a mass of a substance, you can find out how many atoms are present in that. And also you know that if you get a mass of a substance similar to its relative atomic mass, for example, I will get one thing again. In this you can see, if you have 23 grams of sodium, but why this 23 is there? It is the relative atomic mass of sodium. So if you measure 23 grams of sodium in the laboratory, it should have 1 mole of sample. What do you mean 1 mole? Avogadro told that in 1 mole there are 6.022 into 10 to the power 23 atoms or ions or molecules. So here these are atoms, so it should have this amount of atoms, because you can't just count one by one. That's why he gave a relationship like this. So from this, the mass, you have the mass, you have the number of moles, and you have the Avogadro's number here. So from these two relationships, we can make an equation like this. That means if you have a certain mass, if you divide that by the molar mass of the substance, for example, you have here, assume that you have 23 grams of sodium, and you know that they will give you that molar mass thing here. It's actually the atomic mass or the molecular mass, but thing is it has a unit. So molar mass I will put for sodium, it is 23 grams per mole. See that? Now you can see, you can cut this gram to gram and you will get 23 and 23 also cut. You can see here 1 and 1, and the answer will be 1 per mole goes to the numerator, it becomes mole. So you have in this 23 grams, you have here equalize here. You have 1 mole. Very clearly you can understand. So this equation is relating the number of moles. Number of moles is represented by letter N. Mass of the sample represented by M, and the molar mass, or what you call atomic mass, or the molecular mass, is represented by capital M. So this equation is a very essential equation for the future grade 11 also. So that's the thing you have to understand related to this final conclusion. So to just not to learn this equation, now we have to learn how to apply the equation. So one application I told you here, I'm giving a chance for you now. You can pause the video and try the questions 1 and 2. Now it's time to check the answer. What is the amount of substance in moles? Here moles, a set of substance, right, in 12 grams of sodium, magnesium. So you are going to find the number of moles. Here if they give a question like this, if you forgot the equation, that will be a great trouble. So how to memorize or how to recall the equation to your brain, this is the method. So what we use here, but you have to know the terms, right? So what is the amount of substance in moles? You can put N in above it, on it, right? Then grams is the mass. Why they give the formula? You need to find the molar mass. So now after you writing this thing, you will get to know the formula like this. You can memorize, you can just recall your memory about the formula. These are the terms they use here. So now I'm applying this here. You can see now I'll use the understanding N equals M over capital M. Now I substitute because we are finding N, so N is subject here, so it's okay. So now number of mass, the amount of mass is 12 grams, and if you go to magnesium, from your you will get this molar mass of magnesium in questions, but it's not mentioned here. I will tell you magnesium is 24, so I'll write 24, the molar mass of magnesium 24 grams per mole. Now I will substitute this thing and solve it. So you can see, you can cut gram to gram, you have a fraction of 1 over 2. So because 1 over 2 here. So that means you in decimals you can say 0.5. The per mole will move up, minus 1 cancel out then. So it becomes mole. You have 0.5 moles. So I'm asking a small question. If that is 0.5 moles, how many atoms of magnesium is present? Then always remember 1 mole contain Avogadro number. If half a mole is there, that means you have half amount of the Avogadro's number. That is the amount of atoms of magnesium in 12 grams of magnesium sample. So let's do the second question now. What is the amount of substance in moles in 10 grams of calcium carbonate? Here this was an element, but here it's a molecule. So you have another step of working, because they are not giving you straightly what is the molar mass of this molecule. You have to find it. For to find it, they are giving calcium is 40, carbon is 12, oxygen is 16. They are giving it. So let's see the first step. First we have to make it satisfied. So we write the equation first. N equals M over capital M we write, but now we have a problem, we don't know this. So find it now, we can find it. I will find it here. Calcium carbonate, this is limestone, right? So I'll write that thing. Calcium is 40 plus carbon is 12 plus, I'll write it here, its oxygen is 3 times of oxygen are there, so 3 times 16. So let's see what we get here. You get here 100 grams per mole. Now I substitute the equation. Now you are happy because you found this M, capital M. So I substitute. The mass is given as 10 grams. So I'll put it 10 grams. And I'll put the molar mass as 100 grams per mole. So you can get the answer clearly, 0.1 mole. See that it's easy to apply. So remember, always check what the question says. Right. Now you try question number 3 for a while. Pause the video and you can try. So it's time to check the answer. How many molecules are there in 5 moles of carbon dioxide? So in this question, carefully read the question. They are asking the number of molecules because it's a molecule. Carbon dioxide is a molecule. So in 5 moles, so we have to go for the Avogadro's constant. Avogadro told that in 1 mole there are how many molecules or atoms or ions? 6.022 into 10 to the power 23. That number you have to remember, right? So it's applicable for either atoms, molecules or ions. Any set contains this much. So if it is 1 mole contain this much, now simple mathematics. 5 moles contain 5 times of this. So the answer will be, you can keep the answer just like 5 bracket 6.022 into 10 to the power 23. You can keep it like that. You don't need to just solve this and get here you get 30 point like that. No need to solve. Solving is not giving you another step mark. So just the student should know the relationship. That's all. That's the thing we get here. So let's try the question number 4. Pause the video and you can try it. Right. Shall we discuss it? So now here, how many water molecules present in 4 moles of water? Here the same thing. If you get 1 mole of water, it contains Avogadro number of molecules. If it is 4 moles, 4 times of Avogadro number. So how easy it is, right? So next one, fifth question. A little small thing you have to do in here, similar to question number 2. So try that. Pause the video. Right, now we can discuss this. Let's see what is the answer you got. What is the mass of 2 moles of urea? Then you have to find it out here also. The same thing you have to do. You just write the term mass M, number of moles 2. You have to write the term, you are going to write the term N, and the formula is given. Why? Because you can find the molar mass from the formula. So this is the relationship you will get here. Easy to write this, then you get the idea what is the equation you have to use. The relationship between these 3 terms is this. Now you are finding the mass. So I subject the mass in the equation. It will be like M is equal to cross multiply M with N. So it becomes N capital M. Now there's another small problem. You have to find the molar mass of urea here. Right? You're going to find the molar mass of urea. So let's find this out. You get 60 grams per mole here. So I use this simple method to find this molar mass of urea. So I can substitute it now easily. Number of moles are 2 moles. Don't forget to write the unit, because the unit is essential to write, because there's a reason I will tell you just now. So it's 60 grams per mole. Right? You can see now you will get an answer called 120. Now most of the students have a doubt what is the unit of this thing. Sometimes they forgot to put the unit, so it's very critical. You won't get the marks without the unit. One method is check what you are finding, because most of the students, they forgot what they are finding, just solve this and get an answer. That's not the thing. You have to be an alert all the time. So mass is the thing we are finding, so it will be grams. So how to confirm that? So you know that I told you to put the units. That's very essential. Don't be lazy. So here moles per mole and mole will cancel out because their opposite integers are present. Then remaining unit will be gram. See, easy to understand that part if you put the units in the substitution. So you have how many masses? What is the mass? So it's 120 grams you need. So that means if you want to get 2 moles of urea, you need to measure 120 grams of urea in the laboratory. Right. Those are the basic questions related to this equation, this important equation. Now we go for small concept questions. Here they are asking how many moles of oxygen atoms does 1 mole of each of the following compounds contain? Here this question, understand the thing properly, they are asking number of oxygen atoms. You can remember the ratio method. That means if I say one example, in 1 molecule of aluminium oxide, this is first one I will get it. In aluminium oxide, the formula is this, because that's why I told you in the previous sessions also, the formula gives you a very important data, that is the atomic ratio. That means you have aluminium is to oxygen ratio will be how much? 2:3. Here it says that in one molecule of aluminium oxide, there are 2 atoms of oxygen, aluminium, and 3 atoms of oxygen. So if we get 1 mole of molecules, there are 2 times of that moles, 2 moles of aluminium atoms and 3 moles of oxygen atoms in 1 mole of aluminium molecules. Then asking the thing like that. So you have to find the ratio here. So first one, the answer will be 3 moles because asking for oxygen molecules, number of moles. So from the ratio is the final understanding. From the ratio you can get the number of molecules. How to get the number of molecules from the number of moles? You know the Avogadro's relationship. 1 mole contains, if they ask like that, right? 1 mole contains Avogadro number. So 3 moles contains 3 times of the Avogadro number. So let's go to the second one. Here ratio is 1:2. So asking about oxygen, so that means 2. So answer for 1 mole of oxygen carbon dioxide molecules, there are 2 moles of oxygen. Here 2:7, asking for oxygen, not for chlorine. So here 7. So that means in 1 mole of molecule of this, you will have 7 moles of oxygen. And this one you can get, I told you in this type of formulas you have to make the empirical formula for this. That means C2H4O2. So asking for O2, right? 2 times O is there. That means 2 moles of oxygen is present in here. And this one also I told you, this bracket means this 2 belongs to this atom and this both. So but asking about oxygen, so just we get it like this. Barium you have 3, phosphorus you have 2, and oxygen you have 2 times 4, it is 8. So the 8 moles of oxygen are present for 1 mole of barium phosphate, right? So like that you can check the answers for those. So hope you got the best understanding for this thing, because this is a foundation lesson for most chemical calculations in the future. So hope you get the understanding properly. So we are meeting with another session, another lesson with another kind of a calculation part in the near future. So have a nice day everyone.